Alright, welcome back to another session of Stack Language, and today we are going to try and optimize a few things in the C compiler because I'm not really happy with the current status of the constants. And let's see what I did in the last day or so, like extra stuff for the Stack compiler itself. So I was adding, the booleans, the strings, same way we did for numbers, and then also worked on conditions and stuff like that. And it was kind of painful to get the strings going because you remember you have to unescape all the characters. So that took a lot of like weird code, which yeah, it's not ideal, but I mean now it does the job, I guess. So that's pretty good. I'm not even sure where it was. I think it's here, string interpret. So it's unescaping the character codes. Kind of sucks, but it does the job. So yeah. But you can see that the code here looks really ugly. So maybe we'll have some feature in the future that I don't know, lets us not have to work that much with swaps and rotates. Not sure yet what it could be, but yeah, I mean, I don't want to like imagine we could add features so much that in the end we get to using variables, right? And we no longer have a stack based language, and we need to find like a fine line between full-blown stack mode, like you just use pops and rotates and so on, and maybe some kind of way of using some variables, but yeah, like still keep the flow of the, like when you work with a language, it has to be stack based because that's the what makes it I guess challenging, right? Like it makes it fun to solve problems in this way. And if we add too many features and make it too easy, then it just becomes a bad Python, right? Like, I mean, with types, but it's just gonna turn into a bad version of Python, basically, or bad version of C, maybe even. So yeah, so let's try to keep it stack based. And yeah, as I said, I added a true to the AST. So or what am I saying? I added the conditions, so the if statement to the AST. So you can see here I made a branch that returns 24, a branch that returns 42, and then we have if true, then it's going to return something, and if false, it's going to return something else. But I hard coded the true value. So yeah, if we try to run actually the thing, is gonna say 24, 27, oh my god, because I have here true. But if I change this one to false and recompile the thing and run it, it's gonna say 42. So you can imagine that this is a program equivalent to false if 27, else 42, free. So this entire AST that we built here, it's equivalent to this thing, right? And then we can change this one to true or false. So that's the idea here. So we made quite a lot of progress, and I would say that the structure for the AST is almost complete. So we only have numbers, booleans, strings, names, and if statements in the language so far. And we have the AST node. Here we need to, I can add some to-dos just to not forget about them. Add position. So we need to keep the position. Plus we also need a ref to the parser when we are gonna add a parser, because we need the file name, right, for errors. So that's what we are gonna need here. Also, I think add inline comments. So I think inline comments like this might be kind of useful, for example, for arrays, saying that, okay, this is an array, but what's the type of the array? It's a stack AST expression. But we currently don't have comments, so we can add it like this. So yeah, I think it's kind of useful until we are able to have like generics and say stack st expression like this or something like that, right? This would be amazing to have, but we don't. So I think inline comments would be really nice. I mean, I'm just gonna remove the to-dos because I don't care about them right now. It's like I can just rewatch this part and remember them. And that's the nice part of recording. So stack st condition, that's kind of complete. We don't need anything else. We have some arrays of expressions here. Then the ast expression is just the kind, and here it's a pointer, right? So why do we have a pointer? Well, we want to simulate an enum in this place. So this is the enum type and this is the enum value. So if we have a number, then we have an ast node, boolean is the same, string name, they are the same, they are ast nodes. But if you have expression condition, you should interpret that pointer as a stack ast condition, right? So it's kind of an enum from Rust or Haskell, right? But we don't have that yet, so we just simulate it like this, which, I mean, could give me some ideas of how to implement enums for this language. It's exactly what we just saw, right? But yeah, we'll see. Then we have the stack ast function, which is missing the arguments and return values because we don't have type checking yet, but we'll add those. And the full ast currently only has an array of functions, but what I think I want the full ast to have is also an array of data. Then it's gonna have the array of preprocessor symbols, and preprocessor is gonna be stuff like imports, and I'm pretty sure I want constants to also be preprocessor stuff. So that's because right now I just make these constants as functions, and you know that's pretty stupid in my opinion, how we are handling the constants. So ideally, when we find this name wherever in the code, we just replace it with 0, right? So that's how the constants should actually work, not having functions. But we'll change that today, I think. I also want to change it in the C compiler because why not? Like, we could just continue with the current implementation of the C compiler and just call it a day and just change this feature in stack, but I think it shouldn't be that difficult, and it might be interesting. Like, how are we gonna handle recursive constants, right? I mean, maybe we won't, and we'll say that we'll do that. It's a to-do for future me, but who knows. So here we then have some literals. Now we get into the assembler territory. So I changed the literals to use constant values, right? So we can have different kinds of literals, number, booleans, and strings, as you remember from the assembly. So if we just paste the assembly, should run the example, right? You can see here that we have literals, right? And they are just like this. And if you have a string, I should run main because main surely has some strings. It's gonna look like this. It's gonna have all the bytes as numbers, and that works. You can trust me. I tested that, right? Yeah, and then it's just the assembler, right? And the assembler has some utils like the function map, so we know because you see here that in functions we don't oh my God, there are so many constants. We don't use, and yeah, the constants, right? I want to make them as literal values, not like that, because that's bad. But we have functions, and the function name is not necessarily the label name, because you can have random characters in these function names, right? So we want to give them a different name. And yeah, that's what the function map does. It maps function names to labels. Then we have the literal map, which maps like a stack literal to its label, right? So it does the same thing like here. And then we have the if counter, which is used if we find some if statements. Really, yeah, here. So in the code, we just count how many ifs we have and generate the labels. It's not really necessary to count up to like 75 because these are private labels. They are starting with a dot. So you can put in each function you can start from 0, but I mean, doesn't matter. It's still fine, especially with macros. I think it's gonna be useful to have this counter, but we'll see if that actually helps. But I mean, it's just easier for me to think about it if we have this thing. So that's kind of it, right? And the rest of the code is just kind of copy pasted between the C code and this. I just had to translate it, right? So what's next is, as I said, to add the data types, the imports, and the constants to the stack.st. And actually, I think that imports and constants are not needed at this stage. Like, they are obviously they are needed for preprocessor and type checking. Well, actually, they are needed just for preprocessor stage, constants and imports. But for type checking, they are not needed, and for assembly generation, they are also not needed because they should already be like evaluated, right, by the preprocessor stage. So we just add data types, which, I mean, oh, even data types, they are needed only for type checking, actually. So yeah, only the functions are needed for this part, right? So data types are needed just for type checking and being and also preprocessor. Let's not forget that we during the preprocessor stage we generate all of those helper constants and functions for data types, right? We generate all the boilerplate basically. So yeah, and then yeah, I guess constants and imports are going to be added once we get to the preprocessor, and data types also preprocessor. Yeah, so okay, right. And then in the main function we just currently we just call to stack assembler emit. We don't parse anything, we don't tokenize anything, we don't read from a file, we just hard code the st. But I think that's all for the updates and the plans in the language. Like it's just translating the C code more or less. And yeah, I just wanted to start from the end of the pipeline to get like, it's much more cool if you actually get results like this, right? So yeah, feels a lot nicer to see like we actually get results like from day one basically. So yeah, let's try to get into the C code and fix the constants. I'm curious how that's gonna go, and if we have time left we can go next with the actual stack assembler? Maybe we can start. I'm not even sure what the next step would be. As I said, I think the next step is to add the parser, the actual parser. So yeah, let's see how things go. So see you in a sec. So we switched to the C code, right? And my problem with the constants, right? So here we emit a program and we make a for loop over the data, over the functions, and over the constants. We shouldn't do this one anymore. I'm not even sure what emit data does, honestly. Oh, we also generate these data like pointer. Yeah, I forgot about these two functions, which are kind of useful. They are the deref and the ref functions for data types. Okay, so actually we need data at assembler stage as well, because we cannot generate these functions. So we cannot generate the deref and ref functions from the stack code. We need to generate that from assembly. It's kind of impossible. And yeah, one thing that's really bad, let's go here when we have keywords. This is a pretty bad situation. So dupe is not really duplicating the value, it's duplicating the pointer. So if we use dupe, we have the same pointer that points to the, like we have two pointers that point to the same value. So if you change the value, you actually change both items from the stack. So I'm not sure if that's intended, like if we want that. It somehow feels like we shouldn't do that, but right now I cannot just change this one to stack pick because we don't know how big the item from the stack is. We don't know that, so that kind of sucks, right? So because we don't know its type, so we are currently stuck with this duplicating the pointer. So we'll see how we can fix that in the future, if it's even something we have to fix. Yeah. So as I said, we do emit const, and emit const sadly shouldn't really happen actually. Right, so I guess the easiest way to reach that is just say, okay, let's delete this part, right? So because you can see like what I did for constants, I just created a function and put all the expressions here, and that's not really ideal, right? So I don't really like this. All right, so that's why I gonna delete it. And then if we go to emitting a name, even this part right here, even this part, I'm checking if we have a constant or a function, right, as a symbol. And constants shouldn't really happen, so we shouldn't find the constants because that's kind of impossible, right? So this one shouldn't really be possible. And if you find the constant, then it's another problem, I guess. Yeah, so I would just say this is not, it's like unreachable, and probably in this case it's not real. So That's one way to think about it. And you can only have function calls, right? So yeah, stack symbol get. I should also have something like stack symbol create or something. Like how do we actually insert a symbol? I don't remember, because we have get, right? But right, and constant is not gonna be a thing anymore, but I can just leave it here because I don't really care. Yeah, that's interesting. I don't see the append function. Or is it like I guess here it's doing that, but it's not really appending a new one, right? So it should be a place where we stack context symbol. Like, I don't see that where it happens appending a symbol. I guess we append here one symbol. Okay. So for example, here we have this function for type checking the constant definition, right? And as I said, I'm not gonna do this one in type checking. We are gonna do stuff like this in the preprocessor stage, right? So again, we should probably just delete this entire part because we are not gonna handle constants in type checking. We are just gonna define the data types, then we are gonna define the functions, and then we are gonna type check the function bodies. So this thing won't happen anymore, right? Because we don't need that part. All right, so now if we run make, I mean, I could just for the names, but yeah, let's see first what happens. Right, so we are gonna have a bunch of errors that say, okay, this thing is not defined, because it's true, it's gonna think that it should be a function with this name, but they are actually the constants. So what we have to do is go in the preprocessor, go over all the constants, and here I'm not sure what algorithm should be used. Like, we are gonna try to figure it out together, like what's gonna be the most efficient way to do it, like replacing all the constants with their values. And we are gonna imagine that we don't have recursive constants yet, because yeah, we don't check that, but hopefully, you know, no one thinks of adding recursive constants. I mean, they're not really constants, they are just macros, right? They are just defines basically, but yeah, we are gonna call them const. So here you can see we go over the imports to build a full AST. Then we have I mean, we did this one, right? We generate all the utils, and now we should have to do go over all the constants and like replace them in the code. So where can we have other constants? Well, the first place is function body, and the second place is other constants. So let's do it the naive way, let's say, constants. And the naive way is going to be having a big for loop over the constants. Like that's my O of n solution. It's dependent on how many constants you have in the program, like how many constant definitions multiplied, well, it's kind of multiplied with the number of constant, it's just added with the number of constants usages, because it's multiplied, like each one has 5 usages, so it's yeah, if you think about it, the complexity is kind of linear with how many like constants you have in the code. So which, I mean, it's kind of the smallest amount, right? I don't see how you can go better than visiting each definition once. I mean, sure, you can build some kind of dependency graph and then actually visit the lowest amount of times, because imagine you have a constant that's used only once and then a constant that's used 100 times. But if you expand the first one first, you only do 101 steps. But if we expand the second one and the second constant uses the first one, you have to do 100 plus 100. So it depends on which order you expand them. So, but you know, that's not that important for stack st const. So let's try to actually I'm gonna call it item. So let's try to iterate over our constants. And what can we do about them is probably something like stack preprocessor expand consts, or expand const, and I'm going to say preprocessor item program. I mean, we could have a separate function, and that's, you know, the better way of doing it. Just have a separate function so we don't clutter this entire thing. So let's get this one, just to, because you can see how big these functions can get. So stack preprocessor expand const. So here we should have stack st const. I'm just gonna call it C, why not? So yeah, and as I said, what do we need to do? Nah, these ones are fine, I don't really care about them. These to-dos, I think we are gonna build a dependency graph and all of this in the stack language itself, so we are not gonna think about solving these problems anymore. We are gonna try to improve them in the stack language after we have for loops and better data structures, because it's gonna be really hard there to build graphs. So as I said, what we want is to iterate all the expression lists, and we need some function to expand constant in expressions, right? So, something like that. So let's do a for unsigned int I is equal to 0, I is less than program And let's expand first in other constants. So as I said, you can have other constants or function bodies, and I mean it's the same thing. In the end you'll see why it's the same thing, so it's gonna be quite cool. So we get the constant, and we kind of want to ignore the calling expand on itself, right? So we don't want that. So we should check if the names are different. Although at the same time, I mean, I'm not gonna do that. Why should we be pussies and be afraid of some stack overflows? It's gonna happen at some point. We are gonna have a while true loop that's never never breaks. We had that in the past. We are still alive. It's fine. Let's ignore that problem. So stack processor expand const in expressions. All right, and here we are gonna put the preprocessor. I don't know why I'm still passing that. The stack constant and item dot expers. And actually, this one is interesting. This one is interesting indeed. So I think I want a reference to item. Well, I mean here it's count, but you get the point. I think we want a reference, and maybe we want to get ref. And you might wonder, why do we want that? Well, if we get a copy and we change, I mean, it's still a pointer too, right? Let me just double check. So no, it's a value, so we would lose the changes. So the idea is that if we get a reference and we change something in this reference, we actually make a change in the program, which makes a change in this program, right? And that means we actually make a change in the program that was argument here. So we propagate the changes, which is what we want. Right, so I think we need to use pointers here. Yeah, right, so if we change this array of expressions, like the values inside of it, then those changes are going to propagate outside of this call, which is what we need. All right, so I mean, let's just imagine that we have this function, and then we have another for loop over the program functions. Here we need a stack sd function funcs and item.body. But you can see expanding in a list of expressions is the same for constants and for functions. So at this point we only have one function to implement, not two, which is pretty nice. So let's define this one, and here we're going to have a dynamic array expers. And as I said, it's nice to have this kind of comment, stack sd expression, to indicate the type, because we don't know, because this is a pointer, we don't know what's the type, like the real type, right? So that's how this function should look like. Damn, it's ugly. Okay, I'm just gonna leave it like that. I don't care. I should install the formatter for C I had one that I liked. I think it's from Clang, but you need some settings to make it actually pretty. Yeah, I mean, I would usually go by, you know, the stuff with the standard for the kernel, but I don't like having to put parentheses. I mean, I don't know why, it's my brain refuses to do that. Okay, expand const in expressions. Like everything else about the, you know, formatting of the code and putting all the variables first and all of that, it's nice, but having to put the curly bracket on the next line, it's so annoying. And it's like you have to do that only for functions, and then for for loops or if statements you have to use this way of doing it. So yeah, I mean, I mean, yeah, why not? Like if the entire, yeah, like your entire team uses that way, then yeah, you have to do it. It's much better. Anyway, so what should we do now? Well, we have a constant, and this constant has a list of expressions. So like, this is a list, right, of expressions, like stack is the expression. Here we have a pointer to a list, so we want to modify this this list. We have expers. It's another list of stack.st expression. What can a stack.st expression be? It can be a name, which is what we are interested in. So if it's a name, if the expression from this list is a name, we might want to replace it with this list. And when is that? When the constant name is equal to the expression name. So in what order should we make the for loop? That's the next question. Usually when I delete from a list or insert stuff into a list, like insert another list into a list, for instance, I would recommend to start from the end, because the I index, like if you think about it, let's say we have a list 1, 2, 3, 4, and you start from the beginning, and when you find an even number, you want to duplicate it. So you have your pointer is on 1, then it becomes 2, and here you add another one, but your pointer is still here, so you go next and you add another 2. Right, you can avoid that by saying, okay, if I added a 2, then I move one more, and then I move one more again from the iteration, so you're safe. Right, so that's how you would avoid this issue. But if you start from the end, you find the 4, you add the 4, you are still here, you make the step, because the for loop, you make the step, you add the 2, you're still here, you make the step, and you don't have to think about that problem, because you add to the right and you move to the left. So that's one way to think about it. So that's why I think I want expression count -1. But I have to use integers. Yeah, I always forget about that. It's annoying, because if I use unsigned and this thing is 0, then you are cooked, basically, because you do an integer overflow and basically I becomes like infinity. If you think about it, it's like 0 - 1. Right, so we did this part. We just need to replace them in the code, so we don't even care that it's function body or oh shit, sorry about that. We don't even care if they are constants or functions. We just know it's a list of expressions and we need to do something with that. So actually, let me just comment this entire thing. So we have a stack st expression expressions. So here I don't think we need to get a reference. I don't think we need to get a reference. I think we just need to get the item. Right. And now is the interesting part. If item.kind is equal to stack st expression name, so if we have a function call, for instance, and names are going to be function calls or constants. I don't think we can have anything else. But yeah, if we find the expression, it's like a name, and also c.name, which is what? I don't know what. It's a stack st node. We care more about the value, which is a string slice, so let's check if the name of the constant is equal to item name value, right? Then replace. Oh, here we need to do a reference and also here reference. So how is replace gonna work? Well, we remove index I, and then we need to shift insert expers at I. That's gonna be interesting. Or I guess shift insert c.expers. I don't even know if we have these functions. Yes, dynamic array delete. Oh, we have. So we have to do a delete on expers index I. Let's see what this function does. So it's gonna take an n. It should do mem copy at some point. Yeah, nice. So basically it takes the destination is, so I mean a drawing would be nice, but let's not. So the dynamic array is basically a big chunk of memory. So destination is going to be index I and source is going to be index I plus 1. So if you mem copy from one to the other, you just shift back once, which is pretty cool. And we also have dynamic array. We don't have insert yet. Shift, we don't. Well, that's sad, we have to implement it. So yeah, I don't think we have. Yeah, we only have append. Well, we could append and swap. But that's weird. So let's just do this dynamic array insert. So we have the dynamic array index where we want to insert, and we should take this one from the dynamic array append. Right. So how is insert going to work? how is insert going to work? Well, first of all, we'll have an edge case where we need to reallocate the array. So I think the easiest way to solve that is to just append item to the end. Then we could use swaps. That's another way of doing it. We could use swaps. But what I don't like about swaps is that we are gonna do a bunch of mem copies, and we can solve it by doing just one mem copy, to be honest. I'm pretty sure about that. We can solve it by doing only one mem copy, or at least close to one mem copy, right? So let's go here. Let me just steal some comments. So insert, it's like shift insert an item to index. It's not setting, but it's shift inserting a single item. We have to insert multiple items, so that's another thing. But we can implement shift insert many as well. That's no big deal. So int result is equal to 0. So how is this thing gonna work? Well, if you want to shift insert the bad index, then you are wrong, my guy. Then I would say to fix the so imagine that our array is at full capacity, right? It's full, and we want to insert an item. That means we are gonna insert our item here, and the entire array gets shifted, so it's beyond the full capacity. So to fix that, what I think I'm gonna do, dynamic array, I'm just gonna append the item to the array. So we just append it to the end, return defer 1. You know what? Compile flags. So really, I have to reopen Vim. Okay, yeah, I mean, I don't know why I don't have LSP here. Isn't it like compile, or is it like compile flags? Oh yeah, it's compile flags. Or no. Then oh nice, yeah, it's compile flags. So we append the item to the array, and this way we are gonna basically have star at the end. But as I said, I don't think we care about like that item. It's not important, right? We don't care about it. So what we are gonna do, we just use it as a size of. So yeah, because otherwise how would you do it? Not sure. Anyway, let's get right back to the stuff. So we have to say count minus index minus 1, and no, I realize that this is not really right, because, well, actually it is, because, yeah, right. So if index is, let's say, equal to count minus 1, this n is going to be 0. So this check is fine. So we want to insert an index. So this n is basically how many items do we have to shift, right? So let's say we have 4 items. We want to insert at index 1. So that's going to tell us 4 minus 1 minus 1. We have to shift 2 items. That's not really true. I should shift 3 items, right? If we want to insert at index 1. So it should be index minus 1. And yeah, basically if somehow this thing is 0, so let's say, how can it be 0? It cannot be 0. It literally cannot be 0. So it's at least 1. Right. So basically, if you want to insert at the end, you should use append, not oh, but another problem. Here we just modify the count. So we should also think about that. We should take this number beforehand. We should take this number beforehand. Right. We take the number, we add our like empty spot at the end, just to solve the memory allocation edge case. And now we need to shift this entire stuff. So how are we gonna do that? As I said, this edge case of n is equal to 0 is impossible. So we just need destination. Now we need a destination, which is gonna be index plus 1, right? It's index plus 1. I'm just thinking, like, what if you want to insert right on the last item? Index plus 1 is going to be this, so it's still fine. And the source is actually index, right? We do the opposite of delete. We expand the array. And you can even think about this, like plus 1, because we insert 1 item. If we inserted 5 items, this would be 5. So you have to keep that in mind when we do insert many. So we increase the index by 1, and between index and index plus 1 are gonna leave our new items. But first we need to memcopy. So we memcopy n items from source to destination. So we shift them to the right. And how many items do we shift? Well, count minus index. And count minus index is, for instance, if we want to insert at index 1, we have 3 items that we need to shift. Okay, so we did that. We basically lost star at this point. We basically lost the star. So we need to put it here. How are we gonna do that? With the memcopy, I think. something like a mem copy. I don't really care. So we need to mem copy. Where do we need to mem copy? At source. Like if we already have src, why not just use it? Okay, what do we need to mem copy? The item and how much item size. So this should actually insert one item. That's pretty cool. And how about insert many? Well, insert many should work just like that. We'll have a pointer just like this and a number of items. All right. So basically insert many. I mean, there I said void pointer, so I don't know if that's important or not, but yeah. Let's also add this one because this one is better, is a better function. Insert many items to index, shift insert. So the logic is going to be similar. If the index is too big, then you cannot really do anything. Return a result, right? And here we need to insert many items. We need to append many items to increase the capacity of the array. So luckily we have that function. Oh, I should have called this one new items. Just to keep it constant. So it's new items. Whoa, what the new items? And the size is new items count. So we just append many here. Nice. Now we need to get the destination and the source to shift, right? And as I said, here instead of adding only one item, we added new items count. So we the destination is gonna be further away. So if you will, right, we had this array, we added 3 items, and let's say this is the source because we want to add at index 1, and the destination should be 3 items further, right? So it's gonna be 1, 2, 3. So we have 3 spaces left, and these are gonna be gone, and then we need to move them into. So it's just like this, but what should we put here? New items and new items count times the item size, right? And I guess, yeah, that's pretty much everything. If you check append many, you can see it's I mean, it's kind of similar, but yeah, we just shift our array with n, because that's how many items we need to shift, and then we insert our items. So that should be shift insert many. Maybe the name should be shift insert, but yeah, whatever. It's kind of obvious what's happening. So okay, so let's go back to the preprocessor. And we should be pretty close to this. So we deleted item I because we no longer need it, and now we just need to dynamic array insert many, where into expressions we need to insert at index I index I, we need to insert new items and the count. So what is new items? Expers dot items. I think I need to pass the address of that, or should I just say void pointer and then see expressions item or like count? Oh, I don't remember. So items is a void pointer, is basically the beginning of the array. Yeah, I think it's kind of stupid that I said void pointer there. It should be just void pointer. Like, the reason why it's void pointer is to tell you that it's an array of something, right? But array of something, that's also just void pointer. So yeah, it's kind of unnecessary to say void pointer, to be honest. Like you can see here that we mem copy from new items. We don't copy from star new items or something. And the same is true for append many. So maybe that's kind of my bad here, right? We append from new items. Maybe this function should actually accept only star here, and like this one as well, right? Maybe that's the way of doing it. And you can see here it's void pointer because it's actually dereferencing it. So maybe append many, I don't know, let's see if we have too many errors in case we no longer have any errors. But like here, for instance, should be enough to only have this. So is it gonna give me an error because of that? No. Perfect. So delete can fail, but let's say it's kind of unreachable because it's only indexed out of bounds. Unreachable cannot really happen. And insert many, we expect this to happen, and if it doesn't happen, then it's an out of memory error usually. Like it could be indexed out of bounds, but it's probably gonna be out of memory. So I think that's everything we need to do, right? So I'm pretty sure this is gonna be quite slow because it needs to go over all the constants, it needs to replace all the constants. So if you have a lot of them, slow. I mean, will it be slower than the Rust compiler? That's the goal. Okay, so I think that's everything for expanding the constants. So let's try to make, and let's try to generate the P. So P is gonna be the AST, right? It's not gonna have anything special. Let's see. Why is it so big? Let's run on examples. Hello world, right? So pretty small. What if we run the preprocessor? You know what? I can make it even smaller. Examples 0, 1. Let's remove that. And let's have const a0. Alright, so if you think about it, it works, right? We don't do type checking, so it's not gonna fail. Buy more RAM. Okay, dude. Okay. 1519. So I was wrong. This thing failed because out of bounds. That's quite interesting. So we deleted expression Oh, and what's funny is that expressions count is now 0. All right, so insert many shouldn't check for this. It should be only if it's bigger. But man, come on. So we check if it's too big, right? If n is 0, then we should stop after this step because we don't have what to mem copy. So just so you understand what the problem was. Whoa, not here. Example, hello world. Here we have only one expression. So if we delete it, the number of expressions is 0. So this check was being true. So I think we need to check if the index is explicitly larger than count. If the index is equal to count, it means you are doing an append. Right, so what I'm going to say is here, if n is equal to 0, where is the delete? So even here is going to be just like that. So I think if n is greater than 0, we are going to do that stuff. We don't have to... So if n is greater than 0, we are doing this mem copy. Because if n is greater than 0, it means that we have to shift the items. If it's 0, then it means we add it to the end of the array and we don't have to shift anything. So I think that's that. So let's go back to main and make that. Right, so now we have a 0 here, which is pretty cool. 0, 1, hello world. Let's try to add more stuff like 1 plus, for instance. Right, we get more stuff. Let's add a, multiple a's. Let's have another const b is equal to a plus a1 plus, and then have a b here, and then another a or something. Let's see if this thing still works. Looks like it still works, right? So I'm pretty convinced that if we do rule 110 with minus p, it's gonna work. And I think let's try to run it. Ooh. Really? We have some constants that are still not expanded. Oh, I didn't read the name, or read only. Oh. Oh, I forgot about the if statements. Funny. Anyway, so this guy was fine. But yeah, that's true. If the expression, so here we check that the expression is a name, right? But what if, so maybe we could do a switch, but no. Else if item kind is equal to stack st expression if or condition. Shit, but that's gonna be so annoying when we have to add more expression kinds. And what if we forget to expand these branches, right? I mean, I don't know what to do. But if you find a conditional, then you need to expand the constant in the if branch. So item conditional if. Wait, condition, what the fuck? Stack expression can be cond. Yeah, that's Oh, it's like this. Huh. I'm curious if this is gonna be fine. Now I think we need to get a ref here. So let's get a ref. Because otherwise, how is this item gonna be changed, right? So void pointer. I don't think it's changed if we take a copy. So we need it like this. Right, and now if we run the P, we shouldn't have it should be like f read. Yeah, here. Instead of that, it's 0. And here, instead of using those constants, is 164 and then logical or I guess bitwise or. Nice. So still works. We actually managed to make the constants actually behave like constants. So they are evaluated at preprocessor stage. So now if we check example asm, we no longer have weird constants in the code. We just have literally the values, right? Which much better. It should be more efficient. So can we check if it's more efficient? Honestly, I think it's like 60 millisecond. I mean, don't quote me on that. Let's go to rule 110. Rule 110, and let's put like 100 more of them. So let's see. It feels a bit faster, to be honest. Not by much, but it's a bit faster. So what was the change, right? We, instead of keeping constants here, we can just remove this. We no longer have constants as symbols, right? Let me just first say that we added a feature add insert many to ds.h. Then this one is not important, and here we feature move const to be more efficient, or I don't know, efficient. Consts keyword expand at preprocess stage, or like const expressions. And what I said is I'm pretty sure we can just remove all of this basically, and it's still gonna work, I think. I mean, we might have some errors. Type check expression name constant. What the fuck? I mean, yeah, this one is not needed, as I said. This one is type checking expression name. Right, so symbol constant, that's not needed. Huh. Right, so this one should still be fine, right? And we don't even need, actually, I think we do something if it's symbol data. Oh, we don't. That's funny. I mean, that's kind of true because we don't care about data. Symbol kind. Anyway. So, yeah. We were able to make those changes. So for the final part for today, I'd say let's just start a bit on adding token kinds to stack.sl, just to get a feeling of how it works. And yeah, try to start on implementing parser, so converting from a list of tokens to an AST. And for now we are gonna skip preprocessor and type checking. I mean, we are gonna skip type checking entirely until we are able to recompile the code, because we already have type checking. So we have type checking from the C code, so we don't have to worry about type checking. We are gonna worry about type checking once we get to using only stack code. So let's see. So I'm gonna say that, how can I say that? This part is stack assembler, basically. This part is related to the assembler. It has the assembler and some other stuff. This part is somewhat related to stack parser, and we'll have stack tokenizer, right? And again, the reason why I made the tokenizer and the parser by hand and haven't used flex or whatever is because now we have to implement it in stack. So if we didn't have experience on how to implement them, then we would be cooked. Let me just say that in the nice way. So yeah, we have the AST structure. We also need the parser structure, so that's gonna be something like data stack parser. I'm not sure what it's gonna have as also, let me just move, and I would like to have all of the data types first, constants first, and yeah, looks much better. So this one is just a helper. All right. So what would be some stuff that the stack parser contains? Well, we can check that from main. Let's see. What is the parser? Well, it has a reference to the lexer, token, next token. It also has the file name. That's interesting to store. And even the nodes are gonna store a reference to the parser and the position, but not yet. So I think yeah, that's that. So to make, like, I'm gonna use this approach obviously with the token and next token, but to make things easy, let's have stack token and stack token. Where is the stack token kind? So it's like stack token. Let's start with functions, or I guess stack token number 0, stack token function, or I guess it's called func. Then we have in. Oh, what would be funny is to have a iota like Golang, so you don't have to say 0, 1, 2. But I don't know how to do that. Okay, then we have token end. Token end, and let's just add something like number 3. So we have a few tokens, right? Let's do stack token is going to be a data type. It's going to have an int for the kind. So here we are pretty close to this thing, and it's also going to have a string size value. It's going to have a string size value. I was thinking if I want to put a pointer or a string there, because if I put a pointer I could have null when it's empty, or if I put a string I can have the length 0 when it's empty, so it works both ways. Let's put a string for the value, because it's like a token, it always has a stuff in it. And we could also have position, right? And that's kind of it, position. So, but for now we can not worry about position, so we are gonna have just kind and that. We could have something like stack token like keyword or something, keyword, so that it doesn't have a value, you know. With kind, let's say, so it only takes the kind and returns stack token. So it's gonna be something like stack token init. Right, but issue is it still has position and I mean whatever. Okay, anyway, so that's gonna be the stack token. Right, we can even have a list of them pretty easily. Right, so in ideally we would have next data stack lexer. The lexer should have, well, if we look at the main, it has a string and it has two positions. So it has a string buffer, it has int position, int read position, and it also has a char ch. Right, it has all of these things. Okay, we don't really have chars, which it's a bit annoying because we need to use character codes, like you can see here. Oh my god, where is it? Like here. Maybe I can somehow generate these with Python or something and then copy paste them in stdlib. I think I'm gonna do that. So let me just copy these into stdlib, and we are gonna put them at the end so we are not consts. Like imagine having 1 million constants. It's gonna make the compiler so slow. Oh my god, it's gonna suck. Well, I mean, C is pretty fast, so yeah. Anyway, so we have all of these things on the lexer, right? And as I said, the parser has a lexer reference, right? It has a lexer reference. So where was the stack parser? It also has a token and the next token. And don't remember the init function. So token is 0 and next token is 0. And then we do parser read, which, okay, yeah, makes sense. Stack parser peak. Yeah, it's like initially the token is gonna be null, right? Yeah, kind of like that. Anyway, so yeah, it should have something like stack token tok and stack token next token, right? That's what it looks like. But yeah, I realized that token is gonna be null at first, which, I mean, I guess it makes sense, but we'll see. So that's that. I guess, oh, another important token here, maybe that should be stack token and the file, maybe that should be the first one, right? And we can maybe do something like, I don't know, like hard code a list of tokens. Um, hmm. We can hard code a list of tokens and then just return that. Right. So maybe it's something like, I don't know. Uh, because I'm pretty sure we're gonna have a function like stack lexer. I mean, we can just copy these functions pretty much. So we need a stack lexer peak, and this thing is gonna take in just the stack lexer, and it's gonna give us a character. Right. So we are interested in this check to return end of file. I guess why not just implement the tokenizer, and then we next time we implement the parser, and we already have the assembler ready to go. So that's not an issue, I guess. We can do it like this. It's gonna be more fun, I think. So we can do stuff like dupe. So we are gonna have the lexer and another lexer. Then I would call maybe yet another dupe, because I can see we use lexer quite a lot here. So even, but I mean, let's just say we call the string. So we say stack lexer.buffer. So we replace this thing with a buffer, right? We can dupe to, so we get lexer buffer again. Now we can call to string.len. So this would give us lexer buffer, lexer buffer. We call to string length, so we get an integer here for the length. We can swap, so we get lexer. We can stack lexer read position, so we get the read position, or I guess read pos, if the read position is greater or equal. So I could say smaller or equal for that check if we have lexer buffer, else v. If that thing is too big, stack token in the file, we return a wait, we should return a character. I'm gonna say byte end of file. Not sure what character that is, but Otherwise we do buffer of read position. So I would, let's just say byte. I would probably swap. I would then read position, right? Read position stack lexer dot read position. So we have buffer and read position, and then just string index, right? And this is gonna give us the byte. I'm not sure what end of file is. Python 3 xchr0. What is there a way to say EOF? EOF character code 26. Yeah, whatever. It's 26 then. It's 20. I mean, I'm gonna add all of them at some point, but yeah, it's gonna be interesting about these ones. Letters, easy, but the rest of them, yeah. So that's how we do lexer peek. Lexer read, let's see. So lexer read, whoa, no. Function stack lexer read. We have a stack lexer and we return integer. So I would probably dupe just to have lexer and then apparently call stack lexer. Oh, you know what I like to do? Actually put like a, you know what, just to annoy people, I'm gonna use comma stack lexer.peek, just to feel like we have so this is gonna be a char. Interestingly enough, we need to dupe 2, so we have lchr and then say stack lexer dot ch dot set. So we remove these and we have stack lexer and char. Right, we just set the lexer character. Now I would probably just swap. Maybe I would swap even here. Because chr is the output, so anyway, let's dupe, for example. So we get ll, then I'm gonna stack lexer dot read position. So this is gonna give me air position. Then I can dupe to stack lexer dot pos dot set. So that's gonna duplicate and then remove them. So we are left with this stuff. All right. Then chr stack lexer airpos. Yeah, that's fine. Then I can do 1 plus, so we have air position plus 1. Then I can dup 2 and then stack lexer dot read position dot set. So we are still left with this stuff, which we can pop twice. So we are left with chr, and that's the return. I think it looks pretty nice. So that would be how we read one, like read and move. Right, read and move. Skip white space. Let's do lexer init first. Let's do lexer init. Function stack lexer init with buffer, because buffer is the only thing we really need. Right, and so what we are gonna do is set everything to 0. So basically 0 0 0 stack lexer dot init. Right, so we set all of these with 0, and now we need to stack lexer read. So this is gonna give us stack lexer, and the cool part of dup, even though I said it sucks because it duplicates pointer, this is gonna give me lexer, right? And if I do stack lexer dot read, both of them are gonna be changed. So here I'm returning stack lexer, but the stack lexer is modified, so it's not an old copy. So I think it's important to have a dup that duplicates reference and a dup that duplicates just the value. Yeah, because stack lexer read doesn't return the stack lexer, so yeah, at some point you lose the reference. So I think that's the way to do it actually. Anyway, let's see. So I kind of need skip white space, but function stack lexer dot skip shite white space stack lexer, and this is going to modify the stack lexer. Oopsie doopsie. So what are we gonna do here? I'm gonna call to dup, so we have lexer, then stack lexer dot ch, so we have the char. Then I should have a function byte dot is space, so I get a boolean. If that's true, then we stack lexer skip white space, else we don't do anything. I mean, else we pop, because we need to. Right, so that's the idea, but we don't have a is white space. And where could those be? Function byte is space. So what's the ord of space? What's the ord of new line and the ord of tabs? Right, that's what I'm interested in. So const byte. You know what's funny? You can actually just say that and it's gonna work. const byte and then just put a \n, and it's like, that's fine, bro. Yeah. I mean, you cannot put a space, but you can put stuff like this. Space, little. Like that's kind of funny, using a string inside of a byte, but yeah. So is space is actually needing these things. Maybe I should move the byte data type at the bottom. So like data byte is just integer, but yeah, we don't really have a way of signifying that really well, so I mean, it's just integer. So is space, we have to do dup byte tab equals swap wait, so we have int, then we have the \t, we change this to bool, we swap, then I guess here we have bool I, the e thingy, so we dup, we byte n equals swap, so we get the same thing. Do we get bool I byte space equals swap bool I, so then we pop or we or once and we or a second time, and we are left with a boolean. Yeah, so that's how is space should work. So this is skip white space. And I also have another function, skip until new line. Skip until new line. Function stack lexer dot skip until new line stack lexer, and obviously it's until new line or end of file, but that's beyond the point. So what do we have to do? We have a lexer, we dup it, we stack lexer.ch, so we get the character, then we have to dup the character ch byte \n, so we get a new line here. We check if it's equal, we don't have not equals yet, so we get basically if it's equal, then we have to swap. So at the end we have a stack lexer, character and boolean, or I guess boolean and character. So yeah, then I would dup again stack lexer. I don't even need to do that, so it was like this, stack lexer and ch byte back end of file, so is equal to end of file. All right, And how can we could use the Morgan. So if you note the entire condition, it becomes A or B not. So if we do an OR, for example, if we do an OR, we have OR, and then if we do a NOT, we have NOT. If you use the Morgan, you'll see that this is basically ch is not equal to \n, and ch is not equal to end of file. So it's exactly the same condition. So if that's true, we have a lexer. And what we want to do is loop stack lexer.read, right? And then we pop, because we don't care about that, and stack lexer skip until new line. So this is gonna remove everything, and on the else case we also just pop, because there's nothing to do. So that's skip until new line. All right, I think. So let's try to start with stack lexer next. So this is a function, stack lexer next. It takes in a lexer and it always returns a stack token. And that's the important part. So let's loop and stack lexer dot skip dot whitespace. So at this point we still have a stack lexer, and sure, I'd like to save the position. Hopefully it's not gonna suck, but you never know. So I would do and stack lexer.pos. It's the position that we need, yeah. I would even swap, if I'm being honest. Swap, so we have the position and stack lexer. All right. I'm pretty sure we'll need the lexer at some point. So I'm gonna dupe again and then say stack lexer.ch. So we have position, stack lexer, character, and now we need to do the if statements. So if character is equal to end of file, we have position and stack lexer and the character, else v, and at the end we need a stack token. So that's what we need to get. So stack token, we can also add position now. Nice. So if we find byte end of file, we can just pop 2. We have the position added. We need to add the kind. So I'm gonna say stack end of file, stack end of file, and we need a value, which is gonna be an empty string. And then we need to rot and stack token init. Stack token dot init. So that's how I would do this part. Now to check, for instance, for parentheses, we could, so byte, and I can just I cannot let's say L parent. I cannot because this is not part of identifiers. Parentheses and commas are not part of identifiers in stack because they are needed elsewhere. I mean, I'm yeah, just so you can forget about white spaces, right? So if it's equal to L parentheses, we still have the same stuff. So again, we pop to stack token L parentheses, nothing, rot stack token dot init. Yeah, and on this case, if it's on the else case, we should have stack token. Is it illegal? Is it illegal token? I don't remember. Yeah, it's illegal. I'm gonna make this one. See, like, would be cool to have some kind of automated enumerator. If it's on the else case, we are gonna do pop2 stack token illegal. I'm not gonna pop2 actually because the character is useful, but we don't really have a way of converting byte to, like, we don't have ord. We'll see how we can do that. So I wouldn't really pop2, but swap pop, right? And now we have position character, so I could even int.show, so it's position character string illegal, position character string position character string illegal, so I have to rot, right? I think it's like swap and rot or something. I'm not sure. Let me just think about it. So we have position lexer character, so we show it, so this one is now a string. We swap and pop, we add kind, so we want kind to be first, chb second, and position to be last. So if I swap and rot, we should put this one first, and then when we rot, we move this one first. Yeah, swap rot and then stack token.init. So that's how we would run stack lexer next. Now, like, it's a good start. Like, you get the point of doing all of these. Let's just go to the main function. Let me just comment all of this out because I don't really want to lose it. And let's try to have something like parentheses, hash symbol, and that's it, because L parentheses is a tokenizable thingy. So then I'm gonna do stack lexer init with buffer, stack lexer init with buffer. So this is gonna give me stack lexer. So I can do Maybe I can do a function stack lexer show. Right, that sounds fun. Stack lexer show or stack lexer dump. Stack lexer dump. Wait, and this one should be stack lexer.next. That's not stack lexer and doesn't do anything. So I need to stack lexer next. Stack lexer.next. Well, dupe and stack lexer next. So we get lexer token, stack lexer and token. Then for this token, I'm gonna do just token kind. So stack token.kind int.show, put a new line, string.concat, string.std out. So just removed it. Stack lexer. Maybe it's a better idea to also dupe it so that we still have the kind. Well, dupe it here so we still have the kind. Right, and now if the kind is end of file, we stop. So stack token end of file equals not. So if it's not equal, then we go again. So if it's not equal to end of file, we say stack lexer dump, else pop v. So this returns nothing. Okay, so let's see what errors do we have, because we are gonna have some errors. 39. Expected or has been matching R expected bool but got int. What? Oh, it's because I duped the end of file thingy, so it's not really right. Right, so we dupe stack lexer ch, then we dupe the stack lexer swap, then here we have a stack lexer bool ch and another ch, then we put end of file, we check for equals, so we have another bool. So then we have to swap, so we have bool and ch, so then we can pop and then or and then do all of that. Nice. Line 45, like using this shit, it's so nice. Okay, so here we have to pop the integer 55. Here we don't have byte left parenthesis, so let's just, I was like, what the fuck? Python 3 was the ord of left parenthesis 40. Let's keep them alphabetical. Yeah, I'm gonna add that at a later stage, but oh, I don't have stack token lparen now. Const stack token lparen is gonna be a 6, and you know what? I think I'm gonna, oops, align them like this, so it's gonna be much easier to just select everything and increase them by 1 or something, right? Okay, and the main has some bullshit return. So this is tag lexer. Let's pop it and let's see if we get segmentation false. Wait, what? I guess that's weird. We didn't return anything, maybe. Yeah, we didn't return anything. Okay. So, oh, I guess we don't even want that anymore. We just want to see the run of example. So here we have stack lexer. What happens if we dupe and then say stack lexer dot next? We get a stack lexer and the stack token, right? We get a stack token. Oh, I could just say stack lexer dump. Okay, we get this stack lexer. Shit. Okay, I mean, at least it's pretty fast. So, if we get illegal, oh, what I forgot here is to actually read the, so here we need to do a pop of the character because we don't care about it. Then we need to stack lexer.read pop, and if we check in main.c, you can see that. Where does that happen though? So we read once. Almost everywhere we read once. It depends, right? So it depends, but I would say, and this is what we need to do. So here we convert, actually swap, and instead of popping, I'm gonna do this stack lexer read. So read from the lexer, then we pop the result, and then we put token illegal 6, 1, and 0. So we get left parenthesis, illegal, and end of file, which is exactly what we wanted. So that's pretty nice. I could even do something like where is this function? Where is this function, right? So this one here is stack token kind dot map, and it takes integer and returns a string, let's say. So we dupe, then we say if it's equal to end of file, if it's equal to end of file, we say like what, end of file, right? Else dupe. So I'm just gonna put illegal is equal to if illegal, I guess, right? Let's just copy all of this. it's gonna be quite a lot of them, so if you have function, it's func. I think, yeah, if it's in, it's in. If it's n, it's n. If it's number, it's number. It's L parenthesis, it's L parenthesis. And on the else case, it's a panic for now. And then you have to put 1, 2, 3, 4, 5, 6, 7. So here, I guess we also have to pop the number. And here we need to panic, pop, and the random string, just so it stops complaining. But that's kind of how we map the stack token. Right, so I would use this one in dump. So instead of int show, I'm gonna put stack token kind map. So now it's gonna say shit, line 13. Or what? Parentheses illegal and then the file. So that's we kind of have a tokenizer now. We just have to finish it. Right. We also have a assembler. We have a small part of tokenizer. We'll have to implement the parser, and I mean we're pretty close, right? If you think about it, like finishing the entire compiler with all the type checking and the nice preprocessor is gonna take some time just to get to the same stage we are currently at. But then maybe we can add more features. So I think we had a pretty good progress, and yeah, let me know what you think about what we achieved so far. If I don't know, you want maybe to have like intermissions while I work alone off screen on this compiler, or if you still enjoy like even though it's hard to follow, I think, because you maybe don't know the language at all. Like, yeah, I mean for me it's easy because I know it. I try to assemble it, but I mean it would be interesting to know that. So yeah, other than that, we'll see in the next one. So see you.